Hi everyone, welcome back to the channel. If you haven't done so, please consider subscribing and help me out to keep things going. So this video is a continuation, a part 2 of a previous video where I introduced network diagrams using a No Man's Sky dataset that I got from some fan's page. And what we're doing in this video is to take a little bit deeper look at that as a different type of network diagram. Specifically, using the network D3 library with R, we looked previously at the simple network function, but now I'm taking a look at the forced network function, which offers a little more control and sophistication. However, it also comes with some added complexity. But let's go ahead and get started. So in the first video, we ended up with sort of a simple data set with to and from columns. That is, columns that described inputs and outputs and connections. And it was really straightforward, 2 columns, one called to, one called from, and that was all that was needed to generate the diagram. However, forced network has a little more complexity required. So now we'll look at how that's created and how that comes together in a final visualization. So first thing, I create a vector containing all unique elements from the to and from data, and note that they're being converted to factors. So this is essentially just a list of factors of all of the unique elements that are present in the data set. So we are looking at essentially craftable recipes from the game, and so this is a list of all of those elements with a few new ones that I added. So if you look in this quick example, this preview of the dataset, you'll see one called ammonia_recipes. That is going to be the very top level node for the cluster of recipes that produce ammonia. And so here are 4 sub components to that head node, and each one of those will have their own individual recipe made of other ingredients or components. So I did generate some to add a little more organization to the network. All right, so the thing that you have to do for this particular function is create a separate data set containing all of the nodes, basically all the players in the network, and then another data set containing the information about how they connect to each other. It's not enough to just have a to and a from column. You have to separately describe who's there and how they're related to each other. So the first thing that I'm doing here is manipulating the nodes a little bit. And so the list that was just created are essentially the nodes, but what I'm adding here are 2 other columns, one called group and one called node size. To do this, I want to take a step back and think about how we want this to play out. So the final diagram here, compared with the one previously, will have colors and some differences in the size of the nodes. So I wanted to play with that a little bit more and add a little more complication to the final product, which is nicer, hopefully. And to do that, my vision is to create a group for all of the base elements that are components to different recipes, and then I want to separately group the created recipe, the indexed recipes 1, 2, 3, 4, etc. And then I also want to have a different group for those very top level nodes that connect all of those recipe iterations together. So, like I used in another example, if you have an apple group, and then you have 5 different ways to make the apple, and then you have all the components underneath it. I want those to all be separate groups so they can be styled differently in the final visualization. So to do that, I first take this list and split it so I only have the components that do not have an underscore, which is a way that I had titled all of those indexed recipes and the top level nodes. So the code here is essentially to take my nodes data set or tibble and then filter it using some pattern recognition with the string matching, and then take the opposite of that. So I'm looking for everything that does not have an underscore. And then I'm using mutate from dplyr to add the group. I'm just setting it equal to 1, and then node size also set equal to 1. And so that's what this looks like. And so we get a tibble back that has our factor list, and then numeric values of 1 for each group and node size. And then I'm going to look at the elements that have an underscore in the name. So we're splitting out these top level nodes that have that underscore. These will be grouped separately. So we have the base elements that are grouped in 1, and then everything else will have its own separate group. So imagine we have a multitude of groups with different colors for all these top levels. And so to do that, we split it out the same way. We're just looking for that underscore, and this time we're looking for elements that have that underscore in the name. And then below that, we have to use a little bit of logic here. So my issue here is that I need to split out all of the top level nodes and their iterated recipes all in the same category somehow, so that they all get the same color. I want everything that is essentially aimed at making the same product to have the same color. But the problem is there are tens of these, something like 60, 70 different recipes. So it's a little bit of a challenge, and I wanted to do that programmatically. So what's a good way to do that? Well, I thought maybe I could use the first few characters in each of those names. So the first few characters of ammonia would be the same, right, for every iterated recipe, but also the top level node. And it would be unique enough that it doesn't appear in these other elements. A single letter wouldn't be unique enough to do that, but the first 5 should be good. So the first thing that I do here is to just create a very small data frame containing those first 5 elements of each string of those names. And then I group those by value, and then using this current group ID function, I'm able to give a numeric label to each one of those. So if you see the word apple 4 times, it will give you 1, 2, 3, 4 in order. And because we already have a group with group ID 1, I wanted to offset all of these by 1 so that it's 2, 3, 4, 5, 6, 7, etc. And so this first result is sort of an intermediate step, but we can see the first 5 characters of the elements and the group ID 2, 3, etc. And then that information can be sort of pasted back to the actual labels that we want to use. So I add that group value to the nodes information. So now I have the nodes and their appropriate group identifier. One thing I did a little beyond is to split out the very highest nodes that are sort of the parent node over the iterated recipes. And I wanted to give them a separate value so that that node size could be even larger than the iterated recipes. So to do that, there's a little matching step here. So first of all, the node clusters tibble that I'm creating gets a node size of 10 in there for everybody. And then I'm looking in that list to update the current value for every label that matches a given string. And I'm using this string recipe, and this grepl function is something that can be used for string matching. So combining that with an if-else statement, the logic is look at the cell, look at the label. If it contains the string recipe, then we're going to give it this value of 100 for the group instead of 10. And so that just updates it. And if that doesn't exist, just give it the existing value already, which is 10. And then that produces this tibble, which gives us all of our labels with all of the updated groups and the node size. And remember, we already have one with all the base elements and the group and node size for those. Remember, those are both set to 1. So the goal here is to bind these 2 data sets together to get one larger data set. But now everybody has the correct group and node size. So this is a really simple one here, but again, we use bind rows to just sort of stack these two data sets together. And then I threw in this additional arrange based on the name just to sort them. So now we see a sorted table that contains all of our values and the group size and the node, and you can see that they're 1, 10, and 100 for the node sizes, and the groups were 1, 2, and beyond. So now the data need to be converted a little bit for the two-part input. Remember, this particular style with the force network function uses multiple inputs. So it needs these separate data frames for the nodes or the players in the network, and then the links or edges or connections between all of them. And so to do that, I looked online and found this nice little method. And so this was suggested by C.J. Yetman, and it converts the existing to-from data to numeric values. So this is his approach here. And what it does is it produces this list of, or a data frame of these connections, but they're numeric. They're not the labels like we saw with the simple network. So it just gives a number to each one of these elements, and then it looks at the connections between them and then matches everything together. So it's essentially a numeric version instead of a text version. And so we have all the text nodes, we have all the numeric links, and now we can make our final plot. And so the plot itself looks very similar to the simple network, but here we have the nodes defined, the links defined, and then the more complex part here is that we have to label the source target information from those. We're using those column names, the value, which we set to value, node ID, which is the name, the group, which is group, and then the node size, which we called node underscore size. There are also a few other arguments you can fill out here if you want. I'm using this charge value of -20 to sort of push the network apart a little bit. I set zoom to true so you can zoom in on it, and the opacity is set to 0.8 so they look a little bit see-through to give it a little more interest. And then here is the final result. It's a little complicated. You've seen that before, but there's more information here with the color, and hopefully, that might be more interesting somehow. You can also see that some of these groups are hanging out by themselves over here. So let's just zoom in on one, and this is silver recipes. And so silver has 3 different ways it can be made. It's running away from me. But you can look and see those different elements that it's made from. So that's essentially that. And if you want, you can export this file. There's a simple way to do that with the save widget function, and you can just use the name of your plot if you want, and then give it a file, and that'll kick it out to its own HTML file, so you can load that and play with it. So this is really small and not too easy to view, but if you zoom in, you can check it out and explore and find some interesting patterns. And again, for something with analysis, you would want to do some other type of method instead of this. But this is fun to look at, and it could be useful for some simple networks to maybe see if you can see some patterns visually. So if you enjoyed this video, make sure you hit like and subscribe to the channel, and stay with me to learn more about technology, education, data science, and visualization. Have a great week. Thanks.